Okay, alright, welcome everyone to our second video in a series essentially doing some midterm review for your APSC174 midterm that's occurring on February 11th, or next Tuesday. This video is going to essentially go over proofs, how to write them, what you need to know, and what is the point of a proof. So to start things off, the point of math and this new idea of vector spaces that you've seen in linear algebra as a whole is that we want to be able to formally define math. And if we want to be able to formally define stuff, we should also be able to prove stuff utterly and truly for any single case. Any single statement should be verifiable. And a big part of that is, some notion of equivalence. So looking at this question as an example that we'll eventually be solving, let's just read it real quick. So we have v1, v2, and u, which are vectors in our vector space V, and we want to show that the span of v1, v2, and u is equal to the span of v1 and v2. If and only if, this is equivalent to saying that u is an element of the span of v1 and v2. Now, just a little bit of intuition on this question as a whole. If u is an element of the span, that means it can be written as a linear combination, and that also kind of means that the span of something that's dependent on two other vectors will not be spanning anything new, because you essentially just added, the same exact object into your span. You're not going to be able to get anywhere else, because everywhere you could have already got with linear combinations, because you have that notion of dependence. So there's this whole idea of proving things generally and other statements implying other statements and statements being equivalent to each other. So we're just going to go quickly through a general framework on how you should probably be approaching most of these questions. If I deviate from this, that's my bad, but I'll try to follow it as well as I can. So number one, you should be writing down the key pieces of information from your question. Like any normal math problem, write down what you know, and here also keyly, what you want to show. So I kind of jumped from point 1 to point 3 here, but you want to know what you have to show beforehand. And the way you can do this is writing down key pieces of information from your question and key theorems or definitions you may need. So in the case of this question, you should probably be writing down, what does it mean to be in a span? What's this notion of dependence? And also, what's it mean for two spans to be equal to each other? Okay? So you want to write down all you know about the question. You want to know all you know generally about the question, so how these different math things work. And then you want to know what you have to show, because unlike in normal math where you kind of intuitively know what you want to show and you just do some calculations and you find out with an answer, you need to know what the answer should be before you even go out to prove it. Because you can't prove anything that you don't assume beforehand, essentially. And then lastly, you should be putting all this together in one coherent proof, and the way you should do that is, generally, you need to state your assumptions and your process and reasoning along the way. So make it as clear as possible to your grader what you are doing and why you're doing it. This will help you get maximal marks, even if you don't successfully prove the thing you were supposed to prove. And then generally, when you're asked to prove something is true, number one, you should actually be proving it. Don't disprove it, for example. I've learned that lesson the hard way. Additionally, if you want to prove something is true, it has to hold always, or in the general case. A way you can do this is you can use arbitrary elements. So in this case, u is an element of our span v1 to v2. U is an arbitrary element of our span. It's not one specific linear combination. It just happens to be linearly dependent on all of those sets. And so you want to use a general u in this case, for example. Now, similarly, if you want to disprove something, so you want to prove something isn't a vector space or isn't a subspace, for example, because let's say it violates closure, then you need to find a counterexample where it violates the rules of what we need. And if you violate one of the rules, you can't exist in that system. So you can't be a vector subspace without having the zero vector, for example. So if you can show the zero vector isn't in your subspace, that's a very easy way of showing you're not actually in a subspace at all. Okay, so this is a little abstract. We're going to dive into an actual example question on how you do this, or this exact question. So essentially, we are going to start with proving question A, which, like I was saying before, is we want to show that the span of three vectors equaling the span of the first two vectors is really equivalent to that third vector already being in the span of the first two. Essentially, adding a new vector into our span doesn't let us get to anywhere new in our space because that new vector could already be constructed by our span. Okay? So the way we're going to do this is through a forward and a backwards implication, essentially saying that if we assume this first part and we can show, the second part over here, then we've done the forward direction of showing that one implies the other. And then if we can go backwards and say that instead, if we start with this assumption and get to this proof, then we've proved the forward and back direction. Essentially, one statement implies the other, and the other statement implies this one. Therefore, those are actually just the exact same statement, and they're equivalent. Okay? So you should probably get a bit familiar with some of these math notations. You likely will be asked a proof question, and it's important to know the basics of the math you're describing and how you can best do that. So starting off with this question, writing down what we know that we have three vectors in our vector space, and we want to show that the span of these vectors is really just equal to the span of v1 and v2. And this is if and only if, that forwards and backwards equivalence relation, where that means that u is just an element of our span. So starting things off, we're going to assume the first part and show the second part, okay? So assuming that the spans are equal, this means that we have something like, for some, we're going to use A, B, C's, and D's, I think. For some A, B, C, D, and E, which are elements of the real numbers, so these are our scalars, and we're just going to use the definition of the span. I guess I can write that out quickly as well, following my framework. So we know that the span of vectors 1 and 2 is equivalent to saying that this is all possible linear combinations, or all alphas and betas, where we have some arbitrary vector, we'll call it u. No, we'll not. That's confusing. We'll call it a, is just equal to, alpha times v1 plus beta times v2. This is what it means for vectors to be in a span. It's all possible linear combinations. You can end up with some arbitrary vector. Okay? Now moving on to actually proving it like we were doing before. So we're going to assume that we have some scalars, and if these spans are equivalent, that's the same as saying that a times v1 plus b times v2 plus c times u is really just equal to d times v1 plus e times v2. Okay? So that's directly from our assumption. We're assuming the first part, and a really easy way of showing that this implies u's in our span is just using the rules of the vector spaces, which are essentially like distributivity and the idea of factoring, which is kind of the exact same thing. And then the idea of, our other things like associativity and commutativity, where we can just solve this as we normally would solve any linear system. And in that, we can do something like c times u, and then move these other two to the other side, and we'll have something like d times v1 minus a times v1 plus e times v2 minus b times v2. So we just move things over. We can do this because of commutativity and associativity of our vector space. And we also have this idea of distributivity. So we can factor elements out. And we can factor our vectors out. And in doing so, we can have a situation where, I guess we'll assume that C is non-zero. Doesn't exactly matter, but sure, we'll say that C is non-zero as part of our assumptions. A non-zero C it restricts our assumption a little bit, but it's really just the same exact assumption because we can find other non-zero elements. Okay? So we're going to have something like V1 is equal to D minus A over C, and V2 times E plus B over that same exact C. Now, since D, A, and C are real numbers where C itself is not equal to 0, this is clearly a real number, and this is also clearly a real number by that same assumption or argument. So essentially, we have the case where U is a linear combination. We're going to call, let this equal to alpha, let this equal to beta. So we have some alpha and some beta that are real numbers, where we have alpha times v1 plus beta times v2. Now, if we go above to our definition, we could probably just sub in u here, because this is exactly what we've shown. we've shown that U is equal to a linear combination of V1 and V2. And that's essentially saying that U is an element of the span, which is all linear combinations. So if it's one linear combination, it's a part of the set of all of them as well. So, this is an exact example of where we assumed the first part of the question. We want to show this equivalence relation, which is that one implies the other. And since we showed that this assumption leads to our second case over here in blue, that really means that we've shown the forward implication, one implies the other, we now need to show the backwards direction. Now, going through the exact same process that we did before, we are going to assume the second part, or that U is an element of our span of V1 to V2, which means that U is equal to a linear combination, some alpha and beta, where alpha times V1 plus beta times V2 is really just equal to our original U, where we have alpha and beta that are real numbers. And now we want to show that these spans are really equivalent. Okay? So I guess it's easy to just start off with what's the span of V1, V2, and U? What is this? Well, it's for some A, B, and C that are real numbers. We have something like A times V1 plus B times V2 plus C times U. Okay? So this is what this span looks like. These are arbitrary vectors, so this is just the general span. And now we're going to sub in our very easy, what is U? So we already know what U is by definition of our question, so we can just say that pretty easily. So we're going to sub in exactly what we think U is, or what we know U is from our question, which is just, an alpha times V1 plus a beta times V2. Okay? Now we can do the exact same factoring and moving stuff around because we're in a vector space. So in a sense, this guy is really equivalent to something like V1 times alpha, or A plus C alpha plus V2 times B plus C beta. Okay? It's quite clear that we essentially just factored these because they all have the common V1 factor, and then we factored all of these because they have the common V2 factor. We brought out the constants. I should say this is also part of that because it distributes. But essentially what we just showed here is that our span of V1, I'll write it out rigorously over here. So our span of V1, V2, and U is really equal to some linear combination where these are real numbers because all those constituents are real numbers and the real numbers are closed, right? That's the whole idea of being in a vector space, that our operations are closed. We're going to add real numbers and end up with real numbers. And since we just showed that these are real numbers, and I guess we could also say that necessarily to be in the span, A, B, and C are arbitrary. They're not necessarily like 0, 0, 0. So since we have something like that, where we have some arbitrary real number scalars times our two vectors, this is really just equivalent to the span of V1 and V2. So in other words, we showed that assuming, I'm just going to call it A, which is our first proposition, which is, that the span of V1, V2, and U is equal to the span of V1 and V2. So assuming A, we could show that B is also true, which is that U is an element of the span of V1 and V2. Or, yeah, something like that. And then we also showed the other way, where if we have our U, which is in our span of V1 and V2, that also means that, we're not adding anything to the span by adding our U vector in, because it's linearly dependent on the others, or because essentially everything that is in U could already be constructed by V1 and V2. That means that these things are really equivalent, or therefore, for V1, V2, and U, which are elements of our vector space, the span of V1, V2, and U being equivalent to, that's this symbol here, is really the span of V1, V2, and U equaling the span of V1 and V2 is equivalent to U simply being an element of the span of V1 and V2. Okay? This is kind of the same idea here. So this is our first question. We made assumptions, we described our thought process as we went, we showed what was going on. I could have been a bit more rigorous in question A in explaining some of the reasoning here. For example, you could say that this step is like distributive law, and this is associativity, and then this is like the closure of the real numbers. So we can explain our steps as we go, and that just makes it really clear to the person looking at our proof exactly what we did. Okay, we're going to dive into the second question, and then that will wrap things up. So we have the same thing over here, and we're going to start with question B, which is asking us if we have W1 and W2, which are vectors in our vector space, such that 2 times W1 plus W2 and W1 plus 2 times W2 are linearly dependent, then we want to show that W1 and W2 are actually linearly dependent as well. So this is going to kind of follow from the same notions of, okay, we have scalars, we can swap a lot of these operations, we can factor out W1s and W2s, and they'll still be multiplied by some scalars, therefore they're linearly dependent. But to first do that, so let's check our framework. So what should we be doing first? We want to write down key pieces of information from the question. We kind of already done that. Now we want to write down, we've already written down what we want to show, and now we're going to write down the key theorems or definitions we might need. So this is going to be the next step, where essentially we want to know what linear dependence is. So linear dependence for W1 and W2. We'll use the arbitrary V1 and V2 and just apply it as we see fit. So if we have linear dependence for this set of vectors, that means that we have some non-zero, alphas and betas, that are real numbers for some alphas and betas where at least one of alpha beta doesn't equal 0. So this is our notion of linear dependence. Let's apply it first to what we have. So we assume that this is linearly dependent. Let's write it out rigorously. Assume that 2 times W1 plus W2 and W1 plus 2 times W2, I believe, are linearly dependent. So that's equivalent to saying that we have scalars alpha and beta that are real and at least one non-zero. Where our traditional equation of dependence holds. So we have something like alpha times 2 times W1 plus W2 plus beta times W1 plus 2 times W2 is equal to 0, where, one of alpha and beta are non-zero, right? So we can construct one of them by scaling the other one. Okay, so let's just straight up add and distribute as we're used to. So this is like alpha times 2 times W1 plus alpha times W2 plus beta times W1 plus 2 times beta times W2 is equal to 0. Now we can factor out some elements. So our W1s will look something like 2 alpha plus beta, and our W2s will look something like alpha plus 2 times beta. Okay, and since one of alpha or beta is non-zero, we're going to have something like this is a real number that is not 0 as well, simply because, you're adding two vectors, at least one of them is non-zero, it shouldn't be 0 as well, unless we're living in the case where alpha is equal to negative beta over 2. But I think because we can restrict that assumption, I believe, essentially just by picking an arbitrary, if alpha is equal to 1, that means that beta is really equal to negative 2 type of thing. We can just pick any cases because these two, alpha and beta, are dependent on each other. So essentially what we showed is that when we assuming that the set W2 times W1 plus W2 and W1 plus 2 times W2, when we assume this, we showed that actually W1 and W2 are linearly dependent too. And this is by simply being able to pick, non-zero scalars where we have this equation that holds. So this possibly could have been more rigorous. Maybe you're explaining your steps like I was doing before here, but I think this is, a pretty solid form on how you could answer this question. I imagine this will hold with the solutions, but like I was saying before, if you check, jackswitzer.com, you can check all the solutions and all the questions and work some more of these out for yourself. Okay, this is it for the second video. I will see you all in the next one.